Hello students, we'll continue again with unit number 1 and the next topic, topic number 7, which is construction equipment basics, earth moving equipments, dewatering and concrete mixing, transporting and placing. So equipment for earth moving. The first one is excavators. So these are heavy machines and it consists of a base cabin and a long arm with a bucket attachment at its end. They use a hydraulic system to function. The operator controls the excavator from the base cabin, which is capable of rotating 3600 rpm. The base cabin is placed on a supporting structure with either wheels or tracks. The excavators are widely used in both small as well as large construction sites. So their applications include excavation, demolition, heavy lifting, grading, landscaping, mining, dredging, and more. Now, next, number 2, backhoe loaders. So backhoe loaders or backhoes are tire-mounted machines with a shovel at the front and a bucket attached to a jointed arm at the rear end. They look quite similar to farm tractors and their mobility makes them ideal for use in urban areas. Backhoe loaders are medium-sized machines that can be used for applications such as excavation works, digging trenches, placing pipes, filling up trenches, lifting materials, etc. Some backhoe loaders come with retraceable buckets that can either be replaced with buckets that can Some backhoe loaders come with retractable buckets that can either be replaced with buckets or with equipment used for other construction activities, or buckets of varying sizes that can be used for applications such as digging trenches varying in their width. Number 3, bulldozers, considered to be one of the most heavy-duty machines that can be spotted at a construction site. It's one of the most common applications of bulldozer is moving huge amounts of dirt or soil in large and open construction sites. They have a large metal plate in the front which can be moved up, down, until a certain depth or in a limited range of angles using 2 hydraulic pistons attached to it. Apart from moving soil, they can also be used for rough grading, fine grading, crushing or removing rocks, etc. Next, skid steer loaders. As the name suggests, these are tire-mounted small-sized machines which can skid on their own axis and therefore are highly applicable in space-constrained construction sites. The tread pattern used in their tires ensure that they have minimal impact on finished construction sites and that they limit soil compaction. These machines provide a good grip on snow as well as mud. Most skid steer loaders commonly available in the market can be retrofitted with different attachments and can be used for a wide range of applications such as moving mud or snow, excavation works, compacting soil, drilling holes, lifting loads, etc. Next, trenchers. Trenchers are earth-moving machines which are used for digging trenches, typically to be used for piping, cabling or draining purposes. The material that has been dug up is deposited beside the trench by the conveyor system of the trencher. Different types of trenchers are available which vary according to their applicability, construction requirement, or the sturdiness of the surface to be trenched. So trenchers generally are mounted either on tracks or on wheels. Next, dewatering. Dewatering and construction. Dewatering are terms used to describe the action of removing groundwater or surface water from a construction site. Normally, the dewatering process is done by pumping or evaporation. It is usually done before excavation for footings and will help to lower the water table that might cause problems during excavations. Dewatering can also refer to the process of removing water from the soil by wet classification. Wet classification is a construction process that looks at the size of the particles that make up the underlying soil in a project site and the flow of fluids through those particles. Dewatering activities must be done properly to avoid eroding the soil on the construction site. It is also important to choose the best location for discharge even when you might be far away from water bodies or catch basins. So there are multiple dewatering products that can be used to remove sediments from the pump water, such as dewatering bags. When choosing discharge areas from a dewatering process, do remember the following points. Number 1, water should not be pumped directly into slopes. Number 2, dewatering activities should be directed to a wooden buffer if available. 3, important to pay special attention and discontinue dewatering if the area shows signs of instability or erosion. 4. Channels used for dewatering must be stable and better if they have been protected with grass or vegetation. 5. Should avoid dewatering under heavy rains because the infiltration rate is at a minimum and water will move slower, or just the dewatering process will not function. 6. Never discharge water that has been contaminated with oil, grease, or chemical products directly. In such instances or situations, an oil-water separator may be necessary. 7. Additional permits and requirements may be needed or might be needed from the state, local, or federal agencies. 8. It is important to understand the water table conditions in the area. Perhaps the underground water is always near the surface, so your plan might not work. That is, dewatering may not work. 9. Some pumps are the most common dewatering technique but can handle only a small volume of water. Dewatering methods. Construction dewatering from open excavation or trenches can be done by several methods. However, the simplest of all is the gravity drain using drainage channels carrying away water from the area to be worked to the discharge point. So other feasible ways for dewatering are water pumping, siphoning, or using large construction machinery buckets to scoop and dump water from the selected area. Earth channels used for dewatering could also be used for protected with ditch linings, and additional protection should be placed to reduce water velocities and minimize erosion. It is recommended to build riprap revetment protection with geotextile to prevent additional erosion at the discharge point. Next, concrete mixing, transporting, and placing. In the simplest form, a concrete is a mixture of paste and aggregates or rocks. The paste, composed of Portland cement and water, coats the surface of the fine, that is small, and coarse, that is larger aggregates. Through a chemical reaction called hydration, the paste hardens and gains strength to form the rock-like mass known as concrete. So concrete, due to its versatility and durability, is the world's most widely used construction material. With increased focus on infrastructure and housing activities, use of concrete in various forms is increasing day by day. It's plastic and malleable when newly mixed, strong and durable when hardened. So these qualities explain why one material, that is concrete, can build skyscrapers, bridges, sidewalks, and superhighways, houses, and dams. Concrete can succumb to an amazing number of illnesses as well. So viewed this way, making good concrete is more of a miracle than a routine procedure. But most of the variables can be controlled, so concrete is used in almost every structure built. So it's the second most commonly used material on the planet next to the water. So good concrete is the result of a good planning involving everyone in the chain. There should be a methodology to determine the quality of the concrete produced, but only a few methods and only one atom of standardization was found in the literature. So the methodology to determine the quality of the concrete mix is often referred to as the measurement of the efficiency of the mixer. The efficiency parameters of a mixer are affected by the order in which the various constituents of the concrete are introduced into the mixer, the type of mixer, and the mixing energy used. So nowadays, for most of the construction projects, the concrete mixer machine and the ready-mix concrete plant is used due to faster, cheaper, efficient, high productivity, better quality, strength, and durability. Next, concrete mixing methods and concrete mixers. Methods for mixing concrete. The production of concrete consists of establishing a mixture proportion for concrete and then mixing these constituent materials to obtain a mixture with well-distributed aggregate. Although there has been significant work in understanding the influence of constituent material types and proportions on RMC performance, much less work has been done to assess the influence of mixing on RMC properties. Several processes are commonly used to mix concrete. The mixing is typically classified into three general types: stationary ready-mix concrete, mobile batching mixed concrete. So what is stationary mixing? It is when the concrete mixing process is done at a work site. Stationary mixers are commercially available in different sizes, up to 9.0 meter cube to 12 yards cube. So ready-mix concrete. Ready-mix concrete is typically batched and mixed off the work site and then delivered to the work site in a concrete mixing truck. RMC, that is ready-mix concrete, can be manufactured by using the following methods. Central mixed concrete is a concrete mixed thoroughly in a stationary mixture that is then discharged into transporting equipment. So this transporting equipment can be a truck agitator, a truck mixer operating at agitation speed, or a no agitating truck. Number 2, shrink mixed concrete is a concrete partially mixed in a stationary mixer with mixing completed in a complete truck mixture during its travel to the work site. Number 3, truck mixed concrete is a concrete mixed completely in a concrete truck mixture. The mixing constituents are batched at a plant, charged into the transporting truck, and mixed as the truck travels to the work site. Mobile batching concrete. The key features of a mobile concrete batching plant is that they are able to provide uniform quantities of concrete at the exact time it is required and to the right quantity. Due to onboard computer control systems, there is no wastage in achieving precision in concrete production. Benefits of a mobile concrete batching plant. It is more economical, no time is wasted by waiting for a ready-mix concrete mixture to deliver concrete to the job site, and because they batch exact quantities of concrete, wastage is minimal. Regarding the concrete batching process, we will see few videos for your better understanding. So that's all for this lecture. Please give your name and enrollment ID in the chat box. Thank you.
In this video, we are going to discuss the differences between flat slab system and conventional slab system. So let's begin. Flat slab, conventional slab. System. In a flat slab system, the floor or roof consists of walls or slabs and there are no beams. Conventional slab system, also known as slab beam system. In conventional slab system, the slabs are supported on a beam. Load transfer. In flat slab system, the load from slab is directly transferred to column. In conventional slab system, the load from slab is transferred to beam and from beam to column. Weight. Weight of flat slab structure is quite low as compared to conventional slab structure, whereas the weight of conventional slab structure is more as compared to flat slab structure. Live load. In flat slab system, live load shall not exceed 3 times the design dead load. Whereas in case of conventional slab system, live load has no relation with design dead load. Thickness of slab. In flat slab system, the thickness of slab is large. In slab beam system, the thickness of slab is small while depth of beam is large. Minimum thickness of slab. In flat slab system, minimum thickness of slab is 125 mm. Whereas in case of slab beam system, the minimum thickness of slab is 100 mm. Height of ceiling. Flat slab system provides greater clear ceiling heights. In conventional slab system, the beams reduce the available clear ceiling height. Drop panel. Drop panels are the rectangular portion provided above the column and below the slab in order to restrict slab from getting sheared and undergo rupture. In flat slab system, drop panel is provided above column, whereas in case of slab beam system, drop panel is not needed above column. Ratio of longer span to shorter span. In case of flat slab system, ratio of longer span to shorter span should not be more than 2.2. Whereas in case of conventional slab system, ratio of longer span to shorter span has no limitation. Story height. In flat slab system, floor system requires lesser depth and hence there will be reduction in story height. In slab beam system, floor system requires more depth and hence there will be increase in story height as compared to flat slab. Services. In flat slab system, it is easy to install sprinkler and piping and other utilities as beams are absent. In slab beam system, it is tricky to install sprinkler, piping and other utilities as beams are present. Illumination. In case of flat slab system, illumination is better as beams are absent. But in case of conventional slab system, illumination is not as effective as in flat slab as beams are present in the system. Acoustical treatment. In flat slab system, it is easier to provide acoustical treatment underside of slab. But in case of conventional slab system, it is difficult to provide acoustical treatment underside of slab. Reinforcements. In flat slab system, reinforcements are commonly provided in two layers, whereas in slab beam system, reinforcements are commonly provided in one layer. Earthquake resistance. Flat slab system is less resistant to earthquake as it is less flexible than slab beam system, whereas slab beam system is more resistant to earthquake as it is flexible than flat slab system. Appearance. In flat slab system, flat ceiling is available which gives attractive appearance. But in case of conventional slab system, flat ceiling is not available for flat attractive appearance, so you may have to do false ceiling. Need for construction. In flat slab system, at least 3 continuous spans in each direction are needed for construction. But in case of conventional slab system, construction of single slab is possible. Quantity of formwork. In flat slab system, less formwork is needed. In slab beam system, more formwork is needed. Time for construction. The time period for construction of flat slab system is less as compared to conventional slab system. The time period for construction of conventional slab system is more as compared to flat slab system. Cost of formwork. In flat slab system, formwork is simple and hence it is not costly. But in slab beam system, formwork is complicated and hence it is costly. Cost of structure. Flat slab structure is more economical than that of conventional slab structure. If we compare the cost of basement plus ground plus 3-storied building, the cost of flat slab structure is approximately 16% less as compared to conventional slab structures. Whereas the conventional slab system is costlier than flat slab system. So friends, I hope I have covered all the differences between flat slab and conventional slab system in this video. Like this video if you learned something and be sure to share it with someone who might benefit from it. You can share
Water bodies are a major part of the landscape. Oceans, rivers, and lakes are often beautiful, but they're not necessarily convenient places to build things. Most of our tools and construction materials, not to mention our labor force, work better in the dry. And yet many types of infrastructure we depend on every day, including wharves, bridges, and dams, are founded below the water. How do they do it? Hey, I'm Grady, and this is Practical Engineering, On today's episode, we're talking about different types of underwater construction. This video is sponsored by HelloFresh, America's most popular meal kit. More on that later. One of the major costs of large construction projects on or near bodies of water is how to manage that water. The first thing you might think of when you consider underwater construction is divers. Humans can survive and even accomplish work underwater with the help of scuba equipment that allows them to breathe and stay warm. Professional divers can accomplish a wide variety of tasks like welding, cutting, and erecting formwork and other structures. But professional diving is dangerous, and the types of tools and equipment that both function underwater and can be used safely by a diver are fairly limited. Remote vehicles and submersibles can take some of the risk away, but they're also limited in the types of tasks they can accomplish. So a lot of underwater construction involves getting rid of the water, so you're not building under it at all. In the industry, this is called dewatering, or sometimes just care of water, and it includes a wide variety of construction equipment and techniques that all have a single goal in mind: to allow construction to happen safely and soundly in areas that would otherwise be infeasible or impossible to build because of water. The heart of many site dewatering plans is the Cofferdam, a usually temporary structure built to hold back water from a construction site. Obviously, a cofferdam needs to be a structure you can build in the wet, otherwise you just need another cofferdam to construct it. In many cases, this is simply an earthen berm. You can just dump soil into the water until it creates an embankment tall enough to serve as an impoundment. Once your construction area is enclosed, you simply pump the water out. Of course, soil is somewhat impermeable, so you need to constantly pump out the water that manages to seep through. And uncompacted and saturated soil is not very strong. A collapse could be extremely dangerous for workers below the cofferdam, so these types of structures require careful design by an engineer to make sure they're safe. Besides earthen embankments, there are a huge variety of cofferdam designs that are used on construction sites. Some use sheet piles, thick steel plates that interlock together. These are driven into subsurface soils with a huge hammer to create a watertight barrier. If the soils are too rocky to drive sheet piles, or the depth is very high, sometimes sheet piles are used to create small, individual enclosures filled with soil called a cellular cofferdam. There are also cofferdams built of steel frames with a membrane and even water-filled rubber bags. No matter what they're made from, cofferdams are almost always built to be dismantled and removed after construction. One important use of cofferdams is to build actual dams. In this case, often two cofferdams are necessary to block off the river on the upstream and downstream ends. But when performing construction across a river, obviously impoundment isn't the only necessary activity for dewatering. You also need a way to divert normal river flows around the construction site. This is why many dams are constructed in phases. You can build most of the structure away from the main channel, then divert the river through the recently constructed intake or spillway, and finally construct the closure section of the dam. The Hoover Dam was built in a narrow canyon and needed massive diversion tunnels through the rock on either side. The lower entrances to these tunnels were sealed off after construction, but the rest of the tunnels became a part of the spillways. For certain types of structures, the foundation can be constructed off-site and floated in by barge, commonly called a caisson. A hollow box or cylinder is lowered into its proper location, and then the soil is excavated and removed from within until a sound layer of rock or strong soil is reached. Finally, the caisson is filled with concrete. Of course, that part about excavating down to a sound rock layer isn't as easy as it sounds. In the past, this was often done by workers, which meant that the inside of the caisson needed to be dewatered. And when you dewater a caisson, you create a difference in pressure between outside and inside, with only soil in between. This means a constant battle of seepage flowing in from the bottom of the caisson, or much worse, unstable soils that can rapidly erode and allow the caisson to flood. These problems are what led to the Pneumatic Caisson, a variation on the original design where compressed air is injected into the structure to balance pressure from the water below. In a pneumatic caisson, the air pressure is maintained equal to or higher than the water pressure at the bottom of the structure so that seepage and soil instability can be avoided. It works just like when you turn a cup upside down before putting it underwater, except in this case the cup is much bigger and the pressures inside can be much higher than normal atmospheric pressure. This is why workers on underwater foundations often got caisson disease, the same decompression sickness that divers get if they surface too quickly. The use of pneumatic caissons is fairly rare today because of all the safety issues. In fact, most advances in construction technology with regard to water are not toward better dewatering methods, but actually how to avoid dewatering altogether. One of those advancements is the use of drilled shafts. With special equipment and construction techniques, you can excavate a hole, install steel reinforcement, and fill it with concrete to create an extremely strong foundation system without any dewatering required. Concrete is a lot denser than water, so if you can do it without much turbulence, which can dilute the cement paste and weaken the final product, concrete placed underwater will cure and harden just as well, if not better, than if it were conventionally placed. The main way we accomplish this is through the use of a trimmie, a tube through which concrete is pumped or gravity fed to the bottom of a form. The end of the tube stays below the top of concrete as it fills the excavation, preventing water from washing away the aggregate and